Welcome to Unit 2 of the German Historical Institute's Statistics for Historians course with Dr. Luke Blaxell of the University of Oxford and Dr. Caspar Bielen of the Turing Institute. In this unit we're going to be looking at basic descriptive statistics, the mode, the mean, the median, standard deviation, correlations and scatter plots. When it comes to statistics, you're probably already familiar with the mode, median and mean. But to recap, these are used when you have a group of data and want to be able to make some generalizations about it. You will see here an example set of 13 readings, which are the number of professional police officers per constabulary in the late 19th century, as part of a study of Victorian policing. Turning first to the mode, this is simply the most popular single number. And we find here that there were 17 officers per constabulary in 3 instances, and that's more than any other single reading. Therefore, the mode is 17. Moving on next to the median is simply the middle data point, and in order to find that, you need to rank, usually from smallest to largest, these 13 data points, starting with the smallest one, that's 5, and proceeding to the largest one, 20. And the median one will be the one in 7th position, which will have 6 on top of it and 6 below it. In this case, the median value is 13. Finally then, there is the mean, or the average, something that's very commonly used. This is simply all of the values added together, divided by the number of values. In this case, the mean number of officers per constabulary is 12.7. Now, all of these are descriptive statistics, which simply enable you to describe and thus communicate more clearly what your data shows. This is different from inferential statistics, which we will come to presently, which is where you take data from samples and make generalizations about a wider population. There are several other very simple but important descriptive statistics that are very often used. There are some measurements that relate to the range of your data. In other words, how much variation there is between the data points. A very common measurement is simply the range, which is the largest minus the smallest. In this case, the largest value being 20, the smallest value being 5, the range is 15. A slightly more sophisticated measure of range can be found in the standard deviation, which is a statistic that measures the dispersion of a data set relative to its mean. If you've got low standard deviation, then that means that the values are not going to vary that much from the mean. If you have high standard deviation, it means that the values might be comprised of some very low values and some very high values, which deviate considerably from the mean. Now, standard deviation is probably the first statistic where it's easier to calculate it with the support of software like Excel or SPSS rather than actually doing it longhand. It's very simple to do in Excel. You simply have your data in a column and then insert the following script inside the formula bar, and specifying the cell that your data begins in and the cell that it ends at. You'll then see the standard deviation. In the case of this data on Victorian policing, we find the standard deviation is 4.46. Now, all of these things, much like other statistics such as percentages or percentage change, are there to help you describe your data. Another very useful descriptive statistic is the humble correlation coefficient. Now, this is usually around where the threshold of most historians' statistical understanding tends to be. The correlation coefficient is a way of expressing in one elegant figure the relationship between two groups of data. Put another way, it's simply saying that if one thing tends to be large, then another thing tends to be large or small. Now, my example here is the relationship between the percentage of the workforce that was unionised according to various bands in early 20th century Britain, and the average salary of those workers in those bands. So let's have a look at that data plotted on a simple scatter plot. Now, a scatter plot is simply a graph showing each data point according to its positions on the x and y axis. So we see, for example, that workers in the 0% unionised band have an average salary of 1,000, whereas those in the 90% unionised band have a salary of 2,000. So what we can do, which you can do on Excel or SPSS statistics very simply, and we'll explain how to do this in the next lecture, is simply put these on a scatter plot and you will see all of the points. Now, you may get a fairly intuitive idea as to what the overall trend line is. In this case, it seems it's pretty obvious there's going to be a positive correlation between the unionised workforce percentage and the salary. But you can put a line of best fit in to confirm this. Now, another way of expressing the relationship between salary and unionised workforce percentage is, of course, this correlation coefficient that I've mentioned. And in this case, this data has a correlation coefficient of 0.9. Now, correlation coefficients can be anywhere from -1, expressing an extremely strong negative relationship, to +1, expressing an extremely strong positive relationship, with 0, no correlation in the middle. In this case, a correlation coefficient of 0.9 represents an extremely strong positive correlation. Now, if we hypothetically suppose that our data was actually reversed, you would see on this scatter plot here the reverse of what we just saw there, which would represent an extremely strong negative relationship, in this case a correlation coefficient of -0.9, given I just hypothetically flipped the data on its head. Now, let's suppose that the data is a little bit different in its nature, that there isn't such a smooth and linear correlation between these two variables. So I've hypothetically rewrapped the data with some readings that deviate from the simple, the higher the unionised workforce percentage you have, the higher the salary. And we see here a much more scattered set of data points. And you can see that the line of best fit doesn't hug quite so tightly the data points. There are a few there that actually are quite a long way away from the line of best fit. Nonetheless, the correlation coefficient here is still 0.68, which is still generally reckoned to be rather strong. Finally, for my third example, I present a much more distributed set of data points, which to the naked eye becomes difficult to discern any real correlation. If we use the line of best fit, we find a very, very weakly inclined positive relationship, in this case a correlation coefficient of 0.08. Now, of course, you're probably left wondering, how do I decide what is a strong correlation coefficient and how do I decide what a weak correlation coefficient is? And the answer to that question is there isn't really an easy answer. These kind of statistical thresholds really can vary according to who you're talking to. If you're talking to scientists, scholars in the hard science, for example, perhaps researching a new drug, a correlation coefficient of 0.6 is probably not going to wow them too much. But if you're talking to a historian or maybe even a social scientist, perhaps that correlation of 0.6 or indeed even as low as 0.3 or 0.4 might actually discern something of potential scholarly interest. Now, a very important thing that you can do with scatter plots and correlation coefficients is to try and ask yourself if some of the outliers, i.e. the data points which are wildly high or wildly low, to ask yourself why those might be like that, and whether it might actually be the case that all of the outlying data points might have something in common with them. Now, if this is the case, you can begin to build an argument for potentially excluding those data points as exceptional, or maybe hiving them off to some other kind of area of analysis. And of course, without those outlying data points, you may find that your correlation gets a lot stronger and so therefore might be of greater significance. So for an example here, I'm going to bring in some of my own work, which is about the relationship in the late 19th century between turnout, i.e. the percentage of voters who have the vote who are actually voting, and the success at the polls of the Conservative Party. Now, it's often been hypothesized in this period that when turnout was lower, the Conservatives tended to do better in terms of their percentage of the poll. And there have been various historians arguing one way or the other for some time. Now, you'll see here that the data for a given general election, in this case the general election of 1900, which was really seen to be a kind of an exemplar of this supposedly inverse relationship between turnout and Conservative success. Now, each of the points on this admittedly rather clustered diagram represents the result from a single constituency. And there are around 600 of those in the British Parliament at that time. And they show each result according to the turnout and according to the percentage of the vote that the Conservatives got in those constituencies. Now, for all this data, we found that the correlation coefficient was around minus 0.4, suggesting a moderate relationship, negative relationship between turnout and Conservative electoral success. But on its own, this correlation coefficient not really strong enough to base any really powerful arguments on. But then I studied some of the outliers and found that some of the outlying results on this graph actually came from Wales and Scotland. And so what I decided to do was to separate on the scatter plot the Scottish and the Welsh constituencies to see if I could find any commonality between them. And hey presto, very interestingly, I actually found a sharp positive correlation between Conservative vote share and turnout in Wales and Scotland alone. And so when I looked at England alone, the correlation coefficient improved from minus 0.4 to around minus 0.6, a much more significant negative correlation coefficient. This then rather supported the argument that the relationship between low turnout and Conservative success was primarily an English phenomenon in 1900. And in applying the same analysis, separating Scotland and Wales to other elections in this period, I found that this applied there also. So I think the takeaway here is that even if the initial correlation coefficients are relatively unpromising, you can get a long way by plotting your data on a scatter plot and looking at some of the outlying data points and seeing if there might be a good argument for excluding or separating them. Of course, it goes without saying that you shouldn't invent spurious reasons to ignore or to sideline inconvenient data points, and obviously it's a question of historical judgment as to whether you're able to make those kinds of distinctions between two different data groups.